So today, triple integrals and cylindrical and spherical coordinates. But let's wrap it up by doing one more rectangular coordinates triple integral, because it's a good segue into what's next. So we're going to set up, but do not evaluate, a triple integral that represents the mass of an upper hemisphere. So an upper hemisphere basically means it's half of a sphere. Now this sphere, if you squared both sides and you rearranged everything where you got the x squared, y squared, and z squared terms on the left and leave the constant on the right, this is the sphere centered at the origin of radius 1. So the upper hemisphere would look like that. Now here's the density function, which belongs in the integrand when you're doing mass of a solid. So then how do you iterate this integral? You know, put limits on it. Well, my favorite order of integration when I'm doing rectangular for triple is dz, dy, dx. And dz gives you the altitude change. Since the lowest that z gets is the xy plane, that would be z equals 0. The capping surface here is as high as z gets, and they gave you the capping surface. That's the square root of 1 minus x squared minus y squared, the hemisphere equation, basically. Now, what about what y and x are doing? Well, if you look at the trace that the sphere makes in the xy plane, and so the way you would do that is you would take your sphere equation, and in the xy plane, we know that z is equal to 0. So if you set z equal to 0, that's what's going on. That's the trace that the solid makes as it cuts through the xy plane. So here in the xy plane, the base of the solid here is just a circle centered at the origin of radius 1. Oh, okay. So then what? Well, then you're going to go, okay, if I'm going to have x be the outermost integral, x looks like it's going between -1 and 1, because the outermost integral has to have constant limits only. And then what is y doing? Well, if you solve this equation for y, you'll get plus or minus the square root of 1 minus x squared. So the positive square root is the upper limit on the y. So if you put your little man in here, his head is on the upper semicircle. So that would be positive square root of 1 minus x squared. And the little man's feet are on the graph of the equation y equals negative square root of 1 minus x squared. So this lower limit for y, whoops, would be negative square root of 1 minus x squared. Now this is a triple integral that would be a little bit difficult to evaluate if you stayed in rectangular. You'd probably eventually want to convert to polar, and we could convert to cylindrical, which you're going to learn next. So here we go. Oh, we still have to do average value. Gosh darn it, I forgot. Average value of a function of 3 variables. Oh, I guess we better do that first. So how do you do this? This one's an easy average value problem, sorry. So when you are doing average value for any function, remember, like for Calc 1, if you'll recall, Calc 1 average value, f average, f bar, was 1 over the length of the integral, b minus a, the integral going from a to b dx. And for a two-dimensional, a function of 2 variables, the f bar was 1 over area of a region R, and then the double integral where you evaluate the function of 2 variables over that region. So in 3D, if you're doing a function of 3 variables, f, x, y, z, this guy's average, which you're calling f bar, is 1 divided by the volume of the solid, because the solid is what you're integrating over. Okay, so this is a pretty easy problem. I'm just going to do the setup of it, and I'll let you do the rest. Okay, because they're telling us that the solid is a cubical region D bounded by the coordinate planes. That means it's in the first octant. And then x equals 2, y equals 2, z equals 2 tells me that it's this cube here. When you have all pure number limits, you're going to either have a rectangular box or in this case a cube, which is a box, but it's a nice box. So here's your region D. And we already know what the volume of a cube is. So let's just get the volume of the cube. Well, it's just 2 times 2 times 2, which is 8. So your F bar is going to be 1/8 multiplied with the triple integral of the function. In this case, I should probably say t, because they're giving us the function called t. You know, you're going to put the t of x, y, z here. And then if you choose your order of integration, dz, dx, dy, dx, since we're just a cube here in the first octant, 0 to 2, 0 to 2, 0 to 2. Okay, and then here you would put 6x, y, z. I'm not going to do the rest of this. It's pretty easy. It's just the last example here of a rectangular coordinates triple integral, finding average value. Fine. Okay, now let's do the cylindrical. So in 3D, what do you know so far? Here's what you know so far. You know that in 3D, you can work in what we call the rectangular coordinate system. Fine. So what does that mean? If you locate a point P in the rectangular coordinate system, you identify its location using an order triple, x, comma, y, comma, z. Fine. Well, what's another coordinate system for 3D? Cylindrical. And you're going to love this because you already kind of know it. Really? I didn't learn cylindrical yet. Yeah, you did. It's basically an extension of polar. What? Yeah. So you already know polar. So what's going to happen here is the r and theta that you see in this ordered triple are going to stay the same. It's basically what I like to think of the cylindrical coordinate system is it's polar right here is the xy plane, and somebody jacked on a z-axis, and z just stays itself. So it's basically polar with somebody putting on a vertical z-axis to it. Really, it's that easy, because all of the conversion formulas that you know from polar, still true. They're still good. Nothing new to learn here. Really? Yeah. You know, here's all your conversion formulas. X is r cos theta, y equals r sine theta, which you already know from polar. And then z just stays itself. Z is z. How easy is that? And then to go the other direction, if you already know your x, y, and z, r squared is x squared plus y squared, and tan theta is y over x. You know the drill. And z is just itself, z. So know these conversion formulas because they help. And we'll do a couple of examples for points here, but they're very, very simplistic because it's just a matter of plugging in the formula. So you'll see some of these in your homeworks as well. It's not hard. But let's say somebody gave you an ordered triple that they told you was in cylindrical coordinates. And they said, hey, convert this r theta z to rectangular coordinates. Fine. You already know what your formulas are to convert. X is r cos theta, y is r sine theta, z is just itself, z. So if you honor the order here, r theta z, r is 4, so 4 cos, and then theta is 5 pi 6. And I think cos of 5 pi 6 is negative square root of 3 halves, and then after reducing, your x coordinate will be negative 2 square root of 3. For y, you're going to have r sine theta, so you'll have r sine 5 pi 6, and that's going to be 4 times, I think sine of 5 pi 6 is a half, and that'll just reduce to 2. And z is just itself. Z is just 3, no changes there. So the ordered triple, you always want to write this as an ordered triple, it just looks like this. There's the point in rectangular, same point. No big deal. Now, you have to be careful when you're converting from rectangular to cylindrical, especially for the theta. Why? Because if you solve for theta here, you get arctan of y over x, but you have to be careful because the range of arctan is always going to be between negative pi halves and positive pi halves. And you learn this actually in Calc 2. So if the angle really is supposed to be something else, you may get a wrong answer due to this limitation. So just like when we went over this same issue when we were looking at the two-dimensional vectors and we were trying to find the direction of a vector in 2D, we also acknowledge that you may need to add 180 degrees or pi radians if your point is in quadrant 2 or quadrant 3. Otherwise, leave it alone. The answer is correct. Because over here, if you'll notice, negative pi halves to positive pi halves is going to work for you if your point is located in quadrant 1 or quadrant 4. But suppose your point were way over here in quadrant 2. I hope you can see that this angle here is, I have in pink, that's not an angle that lies between negative pi halves and positive pi halves. Hence, you'll have to add that extra 180 degrees. So this point here, because the 1 square root of 3 is located in quadrant 1, you won't have to add 180 degrees when you're calculating the theta. So here we go. R is square root of x squared plus y squared. So for us, it's going to be square root of 1 squared plus square root of 3 squared, square root of 1 plus 3. Ooh, this is turning out to be a nice number. Does that always happen? Oh, no, it does not. We got lucky. And then theta, which is arctan of y over x. Be careful, arctan of y over x, not x over y. A common student error is to do that fraction upside down. And this is actually, if you can use your graphing calculator on this one, because it turns out to be a nice one. Use it in degrees, and then you can calculate 60 degrees to the correct angle. That's pi thirds. And then z is just z, which is just 2. So the final answer here for cylindrical coordinates is 2 pi thirds 2. And we're done. There's your answer. Now, example 10, I'm putting on here to make a point. This point, which is given to you, you know, here's your R, here's your theta, here's your Z. If you look at the R theta and you graphed it, or excuse me, this is X, Y, Z. Sorry, they're giving you, they want you to convert to cylindrical. Your X and Y, if you graph the X and Y, well, X is negative, so, you know, -1 over here in the world of, somehow went out of the pen, -1 and then square root of 3, yeah, somewhere over here. So here's your point in the XY plane. So yeah, this point, if you'll notice, his angle is not going to be between negative pi halves and positive pi halves. So you better worry. So the R, no big deal. That's still going to be square root of the sum of the squares of X and Y. And that's going to be, again, square root of 4, which is 2. Fine. But the angle, when you do your arctan, if you punch this up in your calculator, believe it or not, your calculator will give you a -60 degrees, which is, you know, down here. That's negative pi thirds, essentially. But that, if you look over here at my diagram, that's not right. Negative pi thirds is not the angle, because the point P, the projection of point P in the XY plane is over there in quadrant 2. So you're going to have to add pi to correct it. You're going to have to correct it. So 2 pi thirds, that's correct. And then Z is just Z, which is 2. So now your R theta Z is 2 pi thirds 2, and there's your final answer for cylindrical. Okay, now that's converting points. Now I'm rarely going to ask you to convert points on quizzes or exams, but I just want to orient you to where you are in the world of cylindrical. More often than not, you'll convert equations, because you'll be trying to convert an integral that's rectangular coordinates to cylindrical. Why? Because it'll turn out to be way easier to integrate when you do the conversion. That's the motivation. All right. So here's some conversion. It's easy. Like this one here, if somebody said, hey, convert that, the intermediate step would be R squared equals 9, square root both sides, boom, you get R equals 3. This one, the intermediate step would be R squared is equal to 4Z, and then they square rooted both sides and took the positive version. Fine. Here, you would get R squared equals Z squared, square root both sides. This one, replace X squared plus Y squared with R squared. Z stays itself, you know, no big deal. You're done. Okay. So let's just do some other ones. Now, folks, this, if you were an algebra student, you're like, hey, that's not even in 3D. Well, sure it is. What's the 3D graph of y squared equals x? You know what the 2D graph looks like, because, you know, x equals y squared is a horizontal parabola. But in 3D, if somebody told you this is representing a 3D thing, you hopefully remember the cylindrical surface from 2 months ago. You first graph the generating curve in 2D, which we did, and then you whoosh it in the direction of the missing variable. Oh my God. So this cylindrical surface looks like that. That's the look of this surface. Ooh, that looks kind of cool. So convert that to cylindrical. Ooh, well, you just replace y with r sine. So y squared is r squared sine squared, and x is r cos. And then you do something that's normally illegal. You divide by a variable, but we're going to assume r is not 0 to make this all legal. And then you have r sine squared theta equals cos. And then typically they like you to solve for r just to clean it up. And so if you divide both sides by sine squared, and then you realize that cos over sine squared is cos over sine times 1 over sine, then you could rewrite this as, and I'll go down here, r is equal to, let's see, cos theta over sine theta is what? Cotangent times 1 over sine, I believe, is cosecant. Okay, so there you go. But there's no z there. Well, yeah, because it would be a cylindrical surface. Now, how about this one? How do you convert this to cylindrical? Well, we got r squared on the left and 2r sine theta on the right. Again, divide both sides by r and assume r isn't 0, and you get r equals 2 sine theta. How do you convert this to rectangular? Woo, this one's a little bit weird. If you take tangent of both sides, I know this seems kind of weird, and you use the conversion formula that tan theta is the same as y over x, and tan pi 6, ooh, well, that's sine of pi 6 over cos of pi 6, and if you use your knowledge of sine and cosine of pi 6, you'll get that. And then I'm going to turn the division of fractions into a multiply problem with multiplying by the reciprocal of the denominator, and then the 2's cancel, and then I'll multiply both sides by x, and it looks like that. Now that's, remember, that's the surface, so you would first graph the line 1 over square root of 3, and then you would whoosh it in the direction of the z axis. So that's that. Now let's do another problem, and I even give this similar problem in my Calc 2 when we're converting between polar and rectangular. The trick is multiply both sides by r. And you're going to assume r is not 0, because you're never allowed to multiply both sides of an equation by 0, just like you're not allowed to divide both sides of an equation by 0. And so you get r squared equals 3r cos, but then the trick is, well, r squared is x squared plus y squared, and r cos is really the same as x. So there you go. All right, we're done with that. Now on the next page, there's some set notation here. What the heck? When do you convert to cylindrical? Like, who cares? Do you always convert to cylindrical every time you get a triple integral? No, of course not. My goodness. Just like you don't always convert to polar coordinates every time you get a double integral. It's similar in that when you convert to polar, when you're doing a double integral, you're only allowed, or it only makes sense for regions that are polar sectors, like circles, parts of circles, pizza slices, those kind of things. Similarly, for cylindrical, the sets that lend themselves really well to converting are this, this, and what the heck is this? I'm just going to do one, and then you look at the answers on the next page for more. R is going between 0 and 3. Theta goes between 0 and pi thirds. If I were to graph that in just 2D, that would look like what? It would look like a pizza slice, where I have an angle here of pi thirds. But then z, the altitude, is going to go from 1 to 4. So on the z-axis, here's 1 and 4. You're going to take the portion of a pizza slice. Boy, this is hard to draw. in 3D that lies a thick slice of pizza here, people. It's a thick slice of pizza. And there's a better picture here of what they're looking like. But it looks like it's lying flat or flush on the XY plane. It really isn't. It's lifted up starting where Z equals 1. And the other two there's the graphs. A cone is a pretty good choice for converting to cylindrical. And of course, a can or a can that has a hollow center is a really good choice for cylindrical coordinates. All right, so now let's do some triple integrals in cylindrical. So if they give you set notation for a solid denoted by Q, and the region R is basically a polar sector, you're good to go for cylindrical. So how do you convert? Here's a generic triple integral. The X, the Y, and the Z, those are going to get converted to what? The dV, the volume element, is going to be, oops, sorry, I didn't circle everything I need to circle there. dz r dr d theta. You're going to replace X with R cos. You're going to replace Y with R sine, and you'll leave Z alone. So that's how you'll convert. Okay, so let's do our first cylindrical coordinates example. It's not, this one's pretty easy. I didn't pick something too hard, but there is a flavor to it that's really common, and you'll probably recognize it because I put one of these similar on the quiz that you took for me today or yesterday. What is that? Power reduction formula. Does anybody remember the power reduction formula problem that was on the quiz that you took for me yesterday? Or maybe
Yeah.
I remember.
Yeah, there was one problem on there that had a power reduction formula involved. Not more than one, but one. And if you missed it, I'm sorry. But yesterday, or if you did it today, the quiz 8 was really a preparation for you, like a dress rehearsal for you for next week's exam. Because it sort of had one flavor of everything. It was a nice smorgasbord of tastes and flavors. And that's similar to what I'm going to do for your midterm next week. There's going to be for sure one problem on there, power reduction formula. So, well, it doesn't look like this problem is going to give me a power reduction formula now. Yeah, I know, not yet. Wait, we haven't done anything yet. First up, how do I know this is even a good choice for cylindrical? Well, one reason is because they're telling you. Ha, no choice there. But if you graph in the XY plane, what's going on with the X's and the Y's, like X is going, if you graph X equals -3 and X equals +3 because of the limits on the outermost integral, I get two vertical lines. Okay. And then if I graph Y equals +√9 minus X squared, I get the upper semicircle of a circle centered at the origin of radius 3. And Y equals -√9 minus X squared is the bottom semicircle. So it looks like the region in the XY plane or the polar R theta is a full complete circle centered at the origin of radius 3. So it's real easy to get your R limits now. R starts from the pole, and blossom out, 0 to 3. And theta is doing a full revolution, 0 to 2 pi there. So I get the full 0 to 2 pi circle. Then what about the Z? Well, the limits on Z are 0 to 9 minus X squared minus Y squared. But if you look at the 9 minus X squared minus Y squared and you factor out a negative from the X squared and the Y squared terms, you can easily convert that to polar or cylindrical rather, 9 minus R squared. So when I rewrite this triple integral, instead of dz, dy, dx, I'm going to have r dz, dr, d theta. Don't forget, be a pirate. And then y squared is r squared sine squared theta. There's your y squared. And then we change all our limits. So the innermost integral is with respect to z. So that's 0 to 9 minus r squared. And then we decided that r was 0 to 3 and theta was 0 to 2 pi. So I give you partial credit if you make it this far. If you can do a conversion, you get some points, okay? Now the rest of your points are evaluated. Okay, before I do, I'd like to combine all of my powers of r into one power of r. And sine squared theta, I'll put it over here to the side, and then I get my r cubed here. And then I got dz dr d theta. Okay, let's do the innermost integral first. Integrate with respect to z. That means you're going to hold r and theta constant. So sine squared theta r cubed just looks like a constant. Okay, fine. So just kind of move it over to the side there. And so the antiderivative is just going to be that constant multiplied with z. And z is going to go from 0 to 9 minus r squared. Okay, fine. So then when you use your fundamental theorem of calculus, you plug in your upper limit, 9 minus r squared minus 0. So it's just going to be the 9 minus r squared only. And now this double integral just looks like a polar, because that's really what it is at this point. So you want to play it safe and distribute your r cubed over that difference before you integrate with respect to r. Sine squared, you don't need to distribute that. I mean, you can, but it's going to be messy. Do you like messes? I don't. So because it's considered just a constant multiple, leave it over to the side and don't distribute it unless you like a pain in the butt. Okay, keep it simple, people. Keep it simple. Oops, I had too many 9s there. That should be just 9r cubed minus r to the 5th, sorry. And then this is really easy to integrate with respect to r. That's just a polynomial, and the sine squared theta is just a multiple. So it looks like I'll get an antiderivative 9/4 r to the 4th minus r6 power over 6, and you're going to evaluate that between 0 and 3. And so you're just going to plug in a 3, 9/4, 3 to the 4th power, yuck, minus 3 to the 6th power over 6, oh, yuck. And, you know, whip out a calculator and figure out what that is, and then use your fraction command. I get 243 fourths, fine, and that's just a constant multiple, so I'm going to put it way outside the integral. And then I'm finally going to integrate the last time with respect to theta. And so you're going to use the power reduction formula. That's what I'd like to see. That's what I want to see. And so I'm sine squared gets rewritten as 1 minus cos 2 theta over 2. And I don't like fractions, so if you don't mind, I'm going to do an intermediate move where I'm going to pull the half out so I don't have to have things look so messy, and really just integrate a 1 minus cos of 2 theta, d theta. And remember, this cosine u equals 2 theta, du is 2. When you put your 2 in and divide out by 2, don't put it way out in front because you don't want to affect the 1. He doesn't need the half. His antiderivative is simply theta. And so after integrating cos of 2 theta, you'll get sine of 2 theta. And you're going to evaluate this antiderivative between 0 and 2 pi. Now quickly, the sine of 2 theta, I hope you can see whether you plug in a 0 or that sine term is going to get be 0 the whole time. So it's not contributing to your final answer. Does that always happen? No, but when it does, that's nice. So the only contributing term is the theta. And so when he takes on a 2 pi, it's going to give you something. And then reducing your final answer to lowest terms, I get 243 pi fourths. And we're done with that problem. Okay, so to recap, when you're doing one of these kinds of problems, even if they don't ask you for a sketch in the XY plane, I would do it anyways, because it helps you decide what the limits are for those other variables, in this case, r and theta. It's helpful. Do it. Oftentimes, I ask you for it too, to get your full points. And then use your conversion formulas. Y squared is r squared sine squared. And then when you were trying to figure out the limits for z, 9 minus x squared minus y squared just easily got rewritten as 9 minus r squared. And then integrate, integrate. And if you need the power reduction formula, don't forget it. Questions?
For the ending part where you did the integral, you factored out the 243/4, and then you have the integral of sine squared theta
Mm-hmm.
on
Right
the
here?
bottom. Yes.
Sure.
How did it go to cosine?
Because if you review your power reduction formula, both sine squared and cos squared have a cosine in there, no sines. You probably forgot.
Okay.
Yeah, trust me. The power reduction formula for both cosine squared and sine squared, there's a cosine here, not a sine.
Oh, that's right. Yeah, it's
And
just
I know
plus
it's
or minus.
weird, and even when I teach this to my Calc 2 students, they always get really messed up too, because they're like, "Oh, you must have made a mistake, professor. Sine squared has a sine in it." No, power reduction formula is cos for both. Weird, huh? Okay, any other questions? All right, know how to do your power reduction formula. Have it handy. Have it handy. Okay, so let's do a My Math Lab problem. That's right. I just took this right out of My Math Lab. Screenshot, baby. So use cylindrical coordinates to find the volume of a solid in the first octant. Keep in mind, that means X is greater than 0, Y greater than 0, Z greater than 0. Does that always is everything first octant? No. But if you see that, that's kind of nice. Okay, a cylinder. What's a cylinder? Well, it's like a Coke can. If I graph x squared plus y squared equals 25, I first graph the generating curve in the xy plane, which is a circle of radius 5 centered at the origin, and then I whoosh it in the direction of the missing variable. So that's a can, and it's also, and we only want to look at the portion of the can that's here in the first octant, which is this portion right here coming out of the page. And then z equals x. Now, folks, this is the capping surface. Okay, and they're asking for cylindrical coordinates here. So in the xy plane, I hope you can see that you are dealing with, this circle of radius 5 here. So you can assume, since we're in the first octant, that means that we're going to only be in the first quadrant. Okay, so R is going to go between 0 and 5, and theta is going to go between what and what? Nathaniel, tell me.
There's okay. Looks like
What,
it's from 0 to 2 pi.
0 to what?
2 pi?
No. What is the angle
Oh,
here in the
my bad.
first
I'm looking
quadrant?
at my bad. I'm looking at the cylinder.
Yeah, I'm looking down here because we're only considering a quarter of the circle there, or
Yeah.
the can. We're cutting the can into fourths because we only want, well, actually eighths, but because of octants.
So that's
So
in pi over
what
2.
is, thank you. Okay, do you see why that's pi over 2? Because they said first octant, which means first quadrant, which means theta is going to go between 0 and pi halves. You see how that works out?
Yeah, I didn't know that first octant meant first quadrant.
Okay, yeah, that's sort of the assumption here. Great. So now you have all these boxes that you have to type in stuff, and they want you to use increasing limits of integration. Okay, fine. So theta, 0 to pi halves. R, 0 to 5. Z, well, we know because we're bounded by the coordinate planes, the lowest that Z gets is the XY plane, which has the equation Z equals 0. Now, the highest Z gets is X, but you don't want to put an X there. Why not? Why is putting an X there wrong?
We want it in cylindrical.
Yeah, cylindrical coordinates. If you're doing cylindrical, I better only see an R, a theta, or a Z, or one of those kinds of things. Now, since we're integrating here with respect to Z, you're not allowed to put a Z on a limit for the same variable of integration. So what are you going to put instead of X, even though that's technically the capping surface and we want to put that there? What are you going to put instead?
Cosine theta.
R cosine theta. Thank you very much. R cos theta, because that's what X is. X is conversion formula is R cos theta. Fine. Now there's an extra box here. What the heck? What do they want there in that extra box?
R.
R. Thank you. Be a pirate. R. Yeah, remember this volume element, this dV, the volume element for cylindrical is the same as for polar, R dr d theta, and they have an extra dz. So you don't want to forget your R. So this is pretty easy to integrate because look, when you're integrating R with respect to Z, R is constant. So you're really only going to worry about, it's going to be RZ. And then when you apply the fundamental theorem of calculus, it's R times R cos theta, dr, boy, I can't write today. Hello, dr, and this should say d theta over here, sorry. And then multiply your powers of R together before integrating with respect to R. And then the antiderivative of R squared is, and I'll put the cosine in front, R cubed over 3, and you're going from 0 to 5, pretty easy. 5 cubed, what the heck? I don't know. Oops, this should disappear. We have
125.
5 cubed over 3, yeah, I think it's 125. And I'm just going to pull the 125 thirds out in front because it's bothering me. And then, hey, what's the antiderivative of cos? Hey, no power reduction formula needed here. That's just sine. And you're going to evaluate sine between 0 and pi halves. And it turns out to be kind of nice because sine of pi halves is a nice number. Anybody know what that is?
1.
Yeah. And so your final answer is 125 thirds cubic units because we're doing a volume here of that solid. And we're done. Okay. So any questions like that? Pretty easy. Now, out of curiosity, Z equals X, you guys should know what that looks like because Z equals X is, a plane. But what if I wrote it as Z equals R cos theta, which is the cylindrical version. So if I go Z equals R cos theta on my coordinate system, do you see it is a plane? Although they drew it as a circle there. It's a plane. It's the cylindrical coordinates equation for a plane, which is kind of cool. Love it. Now, another thing I could do, and this is one of those weird things, what if I do Z equals 1 minus R? That's a cylindrical coordinates equation. What does that look like? Woo, cool, man. It's a upside down cone. That's kind of cool. Love it. So these are this is cylindrical coordinates. Okay, so now let's do a mass problem. So I like to give at least one of these on the midterm, have you set up an integral representing the mass of something. And now you know how to do the mass of a planar lamina, which would involve a double integral, and the mass of a solid involves a triple integral. So they want us to do the mass of a solid. Fine. And they gave you the density function. Great. So the mass is going to look like triple integral over the solid, which they're naming capital D, and then your density function is the integrand, and then you've got some volume element. So this is the generic look for the mass. This is the triple integral representing mass. Fine. They're telling you to do cylindrical coordinates. So, and hey, this is kind of nice because Z is just going from -1 to 2. Fine. So that means the limits for Z are just constants, which is really nice. But what about what's going on in the XY plane? That's always kind of the trick when you're doing one of the cylindrical coordinates, because you're really just dealing with polar with the Z axis jacked on the top vertically. So what about this? 0 to 2 square root of 2 is what X is doing. So if you graphed X equals 0, X equals 2 square root of 2, and what about what Y is doing? Well, if you look, Y is between these really bizarro square roots. Let's just look at one of them. If y was equal to positive square root of 8 minus x squared, if I square both sides of this equation, what the heck? It helps me. It helps me. I'm doing it for a reason. It helps me. If I add x squared to both sides of the equation, do you see that it is a circle centered at the origin of radius what? Be careful. What's the radius here?
2 square root of 2.
Yeah, square root of 8, which is 2 root 2. So it would be the whole circle because they're telling me that y goes between negative square root of 8 minus x squared. That would be the lower semicircle. And then the upper semicircle would be y equals positive square root of 8 minus x squared. Do we want the whole circle though? No, because they're telling us that x lies between 0 and 2 square root of 2. So really, we only want the right half side of the circle. This is the what's going on here in the xy plane. So if I look here and I figure out my limits, I hope you can see that theta is going to go from negative pi halves to positive pi halves with that right half side of the circle. And r is going from 0 to 2 square root of 2. So this is key that you understand this. Any questions on how I got those limits from this right half semicircle?
What did you say that you used to dictate the pi over 2 and negative pi over 2?
Can you see my drawing?
Yeah. That part.
Can you understand that in the world of, you took a trig class, when you're going from here to here, down here is negative pi halves, right?
Yes.
On the positive x-axis, and over here is positive pi halves. And so
Yes.
this whole shebangy right here, you're going from negative pi halves to positive pi halves. Does that help?
Yeah, but how did you know that that was the shaded region?
Okay, well, did you understand all this stuff that I was doing over here?
Yes.
That's how I knew. I'm using all the information they're giving me in the set notation. They're telling me that x goes from 0 to 2 square root of 2. Let's start over. Do you get that x goes from 0 to 2 square root of 2, Nathaniel?
Yes.
On the x-axis? And they're telling you that y, if you look at the set notation on your course reader there, please look at it. The negative square root of 8 minus x squared is the bottom half of a semicircle. Yeah.
Oh, okay.
And the y equals positive square root of 8 minus x squared is the upper half. Well, I thought that's the whole damn circle, right? No. Why not? Well, because they told you what x is going between. So you're not going to take the whole circle. X only lies between these two fences. So that's how I knew to shade in only the right half of the circle. Because remember, when you're shading or sketching in your region of integration, you have to honor all 4 fences. Yes?
Okay.
The vegetable garden has to lie between all 4 fences. You have to honor all 4 of the fences. Is that understood?
Yeah, that's why I was getting. That's what was confusing me.
Okay, yeah, you've got your fences, and they're kind of giving you your fences, your 4 fences, but disguised. It's disguised in the set notation curly braces here. Yeah?
Yeah.
Okay. So honor your fences. And then we're going to start rewriting this triple integral into cylindrical. So you're going to go boom, boom, boom. X squared plus y squared is r squared. Your volume element for cylindrical is r dz dr d theta. And stay with that order too. Do yourself a favor, unless you like pain. Z in the set notation, they already told us, goes from a constant to a constant, -1 to 2. That's very convenient. And R, we already figured out, goes from 0 to 2 square root of 2. And the theta was negative pi halves to positive pi halves. Now, for this integration problem, I like this problem because you have to know something about integration, not hard integration, but you have to have strong integration skills, because that's how the rest of the semester is going to go. But first, I'm going to integrate with respect to z. Good news, because that means this whole integrand looks like a constant with respect to z. So I'm just going to copy it down. It's just a constant multiple. And then the antiderivative with respect to z, and you're going to have z going between -1 and 2, which is pretty easy because that's just going to be 2 minus a minus 1. And 2 minus a minus 1 is just going to be a 3. So pull the 3 out in front and keep going. So now you're going to integrate, and it's supposed to be r squared plus 1. I apologize. I'm trying to go way too fast, but I need to. We're going kind of slow here. I got to get through as much as I can. Yeah, this week's going to be kind of a nightmare. Well, the rest of the semester will too, because we got a lot of work to do. So I'm going to use the power rule with u sub. So when you use any u sub in my class, I want you to tell me your u and your du. Otherwise, you're going to lose a point or two of partial credit. So I do have an r and a dr in the integrand, but I wish there were a 2. No problem. Put one in, provided you divide one out. So just as a side, just some scratch over here, that innermost integral looks like square root of u du right now. So u to the half is what we're integrating, and the antiderivative is 2/3 u to the 3/2. Okay, so you're going to go, all right, 2/3 u to the 3/2, but what was u? It was r squared plus 1, and to the 3/2, and you're going to go from 0 to this yucky number, 2 square root of 2. Oh man, ugh, yuck. I know. And then this 2/3 swings out, but then those cancel. So you no longer have any constant multiple out in the front. You're going to get 2 square root of 2 squared plus 1 to the 3/2 minus 1 to the 3/2. Okay, that's easy. Remember, 2 square root of 2 squared is 8, and 8 plus 1 is 9. So really what you have there is 9 to the 3/2. Which is actually a nice number because that's square root of 9 cubed, okay, which is 27. Oh, this is turning out to be kind of sweet. So what am I saying? I'm saying that you've got 27 minus 1 in your integral, which is just 26. Nice. So what's the antiderivative of 26 with respect to theta? Well, it's just 26 times theta, and theta is going to go from, oops, not 0, but negative pi halves, negative, come on, baby. Nope. Want to do it. No, erase tool doesn't want to work. Okay, so I'm having quite the delay right now. My erase tool won't go away. Sorry. Technology problems, baby. Won't go away. Negative pi halves to positive pi halves. Wow, I'm getting like a 10 or 15 second delay now. Lovely. And that's going to be 26, and I'm just going to write really fast. And on invisible ink, I don't care anymore. I get 26 pi for my final answer. Okay, 26 pi, final answer. We're done. That's the mass of the solid. Okay. So another meme for you. So if you're going to be a pirate, the question is, should you say "ar" or should you say "yar"? Or maybe "har"? I don't know. All three are good. Okay. That could be the debate. We could sit here for the rest of the class and debate which one of those is the better choice to be a pirate. I don't know. It's up to you.
Chat says.
These memes keep me going. Well, I'm glad because, you know, we got to have something. Otherwise, it's zoom, zoom, zoom the whole time. And, you know, we're just zooming away. Okay. So we're done with cylindrical. So what's the point? I want you to get that cylindrical is not that hard because it's just the polar with a z-axis vertically jacked on. Spherical is the one that's a challenge for So if you thought the last thing was challenging, let me just tell you in advance that the spherical gets tricky because it's really weird. Cylindrical is nice because you already had been introduced to polar, and you can think of cylindrical as being polar with the z-axis jacked on. But spherical doesn't have anything to match it up to. So let's start doing the basics. Spherical, it's a new coordinate system to represent 3D. Fine. Why? The motivation is going to be, you're going to be integrating on a region, a solid region, of course, that is going to be either a sphere or a portion of a sphere or something that has some symmetry about the origin. And cylindrical probably won't work. And it's a better choice to convert to spherical. So you don't kind of have a choice. Like, well, I don't want to learn anything new. Well, you know, I'm tired too. So you're going to have an ordered triple, but it's going to be the following order. Row, and by the way, learn how to write the row. I already talked about row because a lot of times we use the same row when we're doing a density function designation. But row is kind of it's the Greek letter R. And then you're going to have two angles. And the row here, row, is a distance that is going to be non-negative. And you can think of it as the distance between the point and the origin. So this right here, this length right here is your row. Now the theta is the same theta you used in polar. Oh, thank God, good news. Something you can relate to. So if you project the P down here to the XY plane, you may have the shadow that the point P makes in the XY plane. I'll call that point P prime. The angle that the line segment OP prime makes with the positive x-axis, which is the same as your polar. That's your theta. That's going to go second. So you know theta already. Thank God it's the same theta as before. And then this new angle, which is called phi, it's also a Greek letter. I know that's a weird looking symbol, but you need to, you know, phi. I like to think of it as a zero with a line through it. This angle is a little bit tricky because it's not an angle you've studied before. If you look at the line segment OP here, which I'm highlighting with my pen, the angle that that line segment makes with the positive z-axis is your phi angle. Now, that angle phi is restricted to 0 to pi. Well, how come? Because the z-axis, if I extend the negative z-axis down here, the most that the angle can be is from here to here. 0, a phi of 0, let's say this point, I'll call him Q. If he lives on top of the z-axis, the phi will be 0 degrees because you're right on top of the positive z-axis. And then if you were a point way down here that lived on the negative z-axis, let's just say R, the angle that you're making with the positive z-axis is pi. So phi can never be negative, and it has to be an angle between 0 and pi inclusive. Theta can be, theta can be almost anything, you know, but theta typically is between 0 and 2 pi. Okay, but it can be negative too. So I'm okay with theta going like, remember we just did a problem where we had theta going between negative pi halves and positive pi halves. That's okay also. So theta isn't restricted. Theta is allowed to be negative if you need it to. Phi, no. Here are the conversion formulas. So instead of writing them down, just look at this. It's weird. X is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cos phi. There's no theta there. Yeah, I know. If you're going from rectangular to spherical, rho squared is x squared plus y squared plus z squared. You already know this one because you know about theta. So you've seen this, tan theta is equal to y over x, same as before. And phi is kind of horrible. It's arc cos z over that horrible square root. And just for kicks and giggles, although I'm not going to do any problems with it, now that you know about the other 3D coordinate system, cylindrical, what if you want to go back and forth between spherical and cylindrical? Because you might, now that you know 3 completely different coordinate systems for 3D. By the way, I don't want you to get too cocky or arrogant. There are actually more 3D coordinate systems. In other words, rectangular, cylindrical, and spherical are not the only 3. There's like parabolical and elliptical and all kinds of wacky other coordinate systems in 3D. Well, how come? Because our physics brethren need it. They like to think in weird coordinate systems. Yeah, so if you're going to be a mathematical physicist, you'll probably get into some of that wacky crap. Anyway, good luck. I'm no expert, so don't ask me any questions about it. I do want to say one thing about our physics brethren right now. In fact, I'll do it by telling you a story. I have a student. In fact, I just got an email from her recently. I had her like 20 years ago. She was an excellent student. She took me for a couple of calculus classes, went on to UC and became an electrical engineer. Fine. I even went to her wedding. It was down in Tijuana, and it was really beautiful. Anyway, good times, good times. So she went to UCSD, and she took me for Calc 3, and we learned about the rho theta phi spherical coordinate system ordered triple. And when she was at UCSD, she was taking a vector calculus class, and I think also a physics class, and she was like, hey, can you tutor me in this? And I was like, okay, come into my office. So she made it over to Southwestern again. And she goes, what the heck? And we noticed that the ordered triple for the spherical coordinate system in different textbooks, typically physics textbooks, the physicists, it's still the same rho, theta, and phi. The definitions are the same. It's not like they changed definitions. But apparently the physics folks, they like to put their phi second and their theta third. Okay, that's their convention. It's not wrong, it's just a different ordering. But the definition for phi and theta is what you see here on this page. So please note that in case you go take a vector calculus class or whatever, and you're like, hey, this is really weird. I don't understand. Let's do some conversions. So they want us to convert a spherical point. That means this is rho, this is theta, this is phi, to rectangular. So in other words, they want x, y, z. Okay, so x is rho, sine phi, cos theta, according to the formula. So for us, that's 8 sine pi fourths times cos 7 pi 6. Okay, this isn't too hard because sine of pi fourths is square root of 2 over 2. Uh-oh. What the heck is cos of 7 pi 6? Ha ha! It's negative. Negative square root of 3 halves. Reduce this to lowest terms. I get negative 2 square root of 6. Well, that's weird. Yeah, a lot of these are. Y, conversion formula. Rho, sine phi, sine theta. No, that's not a typo. That's correct. 8 sine of pi fourths again. Sine of 7 pi 6. Okay, 8 square root of 2 over 2. Uh-oh. Negative a half. Reduce negative 2 root 2. Z, conversion formula. Rho, cos phi. Okay, 8 cos pi fourths. 8 square root of 2 over 2. Reduce 4 square root of 2. Answer, give it to me as an ordered triple. Okay, negative 2 square root of 6, negative 2 square root of 2, 4 square root of 2. Okay, so there's the equivalent rectangular coordinates point. There you go. All the conversion formulas. Let's do one more and then we'll move on to the next page. I'll let you do 21 and 22 on your own. Here they're giving us a rectangular point. That means they're giving us x, y, and z. They want spherical. So they want rho, theta, phi. That's what they want. Okay, let's give it to them. Rho is the square root of x squared plus y squared plus z squared. That's the square root of square root of 3 squared plus 1 squared plus 2 square root of 3 squared. Oh man, what a mess. Okay, square root of 3 squared, that's easy. It's 3. 1 squared is 1. If you square 2 square root of 3, you'll get 2 squared times square root of 3 squared, but that's 4 times 3, which is 12. So 3 plus 1 plus 12 is 16. Ooh, that turned out to be a nice number because square root of 16 is 4. Does that always happen? No, but that's nice. Now, the x and y coordinates, if you graph that in the xy plane, you're in quadrant 1, which is good news because when you get your theta, it does matter what quadrant you're in. And since we're in quadrant 1, we won't have to add 180 degrees, thank goodness. Using my calculator in degrees mode, I get arctan of 1 over square root of 3 is 30 degrees. Convert that to radians, pi 6. Phi is cos inverse of z all over square root of x squared plus y squared plus z squared. Oh gosh, that is one horrible looking cos inverse. Now, good news, we already got the square root of x squared plus y squared plus z squared because that's when we were figuring out what rho was. So we already did that arithmetic. That's a 4. And then z is 2 square root of 3. So this is cos inverse after reducing of square root of 3 halves. And that's going to give me, I believe, pi 6. So my final answer, the spherical coordinates point is 4. Theta was pi 6, and ooh, phi is pi 6 too. Does that always happen? No, but we got lucky. Okay. There you go. And I'll let you convert between spherical and cylindrical on your own. So I'm going to skip these next 2 problems. Don't worry about it too much. Just, use the formulas supplied and plug it in. Now let's talk about equation converting, because that's more of what you're going to be doing when you convert integrals from one coordinate system to the next. Now, this is the key that I really want you to get out of all of these pictures. Look, people, if you have x squared plus y squared plus z squared equals r squared, which is a sphere equation in rectangular, x squared plus y squared plus z squared is rho squared. So you're going to have rho squared equals r squared. And then if you square root both sides, you get rho equals r, or rho equals some constant. Know that that is a sphere equation in spherical coordinates. And the reason why it's such a beautiful thing is because I hope you can appreciate that the boundary of this sphere, all of the points lie a rho distance away from the origin. And that's why rho equals a constant is the equation for a sphere in spherical coordinates. And the reason, again, why that's so beautiful is because if you were trying to integrate in rectangular where something is a sphere, it's a mess. I mean, you have trig sub all over the place. But when you convert the equation for a sphere from rectangular to spherical, it's easy peasy. And a vertical half plane, and we don't do that so much. Cones, yes. Those are pretty typical spherical. Okay, so let's convert a couple of equations that are given to us in rectangular, and we'll convert them to spherical. So how would we convert letter A? Brute force. What do you mean? Well, you have to just plug in the horrible formulas, like z squared, the left-hand side, I know, like z is rho cos phi, so then you square it, fine. X squared, oh, you're kidding me. No, I'm not. The x, remember, was rho, I'll do a little bit backwards. Cos theta sine phi, and you're going to square it. And then the y was rho sine theta sine phi, square it. And then clean this up. Oh man, you're kidding me. No, I'm not kidding you. You got rho squared cos squared phi on the left. On the right, after I do all the squaring, I'm going to factor out a common factor. I hope you can see that rho squared and sine squared phi is a common factor between those two terms on the right-hand side. And then the other factor will be cos squared plus sine squared, but we know that's just a 1. Beautiful, so that's gone. If you divide both sides by rho squared, assuming that rho isn't 0, you're going to get cos squared phi equals sine squared phi. We're almost done. If I divide both sides by cos squared phi, I get 1 equals tan squared phi. I know that's pretty weird. And then I'm going to solve this. I could just stop because that is, I'm done, you know. But a lot of times they'll want you to like solve it for phi. Okay, well, if you, if you did square root both sides like this, and then you have a plus or minus, you'll get that tangent phi is equal to plus or minus 1. Okay, so what does that mean? Well, phi is going to be arctan of plus or minus 1. So what does that mean? Well, there's two choices. Phi could either be pi fourths, and this is the upper nap of a cone. What do I mean by upper nap? It looks like this. The upper ice cream cone pointed upwards. And then the arctan negative would give you 3 pi fourths. So I want you to notice here with the pi fourths, all the points that live on this cone are exactly pi fourths distance, angle-wise, if you will, the phi. Remember, phi is an angle that it makes with a positive z-axis. And then this is the lower nap of a cone. What do I mean by lower nap? It's a downward facing cone like this. That's what that guy looks like. And I hope you can see that all of the points that lie on the surface of this downward facing cone are 3 pi fourths angle away from the positive z-axis. Okay? Fine. Let's just do one more, and then the other sets, I'm going to blow by that and try to get to a problem. So how would you convert? This is a sphere not centered at the origin. How do I know? Because the minus 4z makes it a little off kilter. I could complete the square and get the center point of this sphere that's not centered at the origin. But instead of doing that, let's not do that. Let's start converting to spherical. X squared plus y squared plus z squared gets all replaced with rho squared. Minus 4z, but z is rho cos phi. You're pretty much done. But if you add the 4 rho cos phi, because they usually like you to solve it for rho, divide both sides by rho, assuming that rho is not 0, you get rho is equal to 4 cos phi. So I can do this on my graphing. Oh, it can't do it. Why not? Can't graph equation in this form. Oh man, I just ran into a roadblock. That's a drag. Okay, well, what about if I graph rho equals 4, say? Oh no, it didn't want to give it to me. I don't want that either. It's not going to go. It's gonna think rho is r, so it's not letting me do it. That's too bad. Let's see something here. Well, I've got a lot of cylindrical, but not. How about z is rho equals. Let's see if this will work. No. Okay, never mind. I better quit wasting valuable time. I'll have to go figure out some spherical things to go graph. Okay. There's some other weird sets. I like this one because you'll see this one on an exam. Really? When? I'm not going to tell you when. Just be prepared for it. What is it? It's concentric spheres where it's a shell where your solid is basically found by taking this outer sphere and cutting away the inner core. Kind of cool, huh? Isn't that how they make chocolate covered cherries? Nice. So these are just candidates that are good candidates for spherical. But honestly, I personally believe the only really good candidates for spherical is spheres centered at the origin or portions of spheres centered at the origins. That's how I roll. Okay. Those are the only ones that I usually, and cones can be okay too, but that takes a little bit of work. Okay, now let's, before we finish today, I want to do at least 1 or 2 examples of a spherical triple integral for you, so you can at least get started on your homework and do some of it. Okay, So let's do some review. What's the volume element for rectangular? So if you see dV, which stands for your volume element, what do you think? What do you replace it with if you're doing a triple integral? Anybody remember? I'll check the chat. Nobody knows, huh? Does anybody know what the volume element is for rectangular? You just took a quiz with me.
Theta.
Does anybody want to learn about triple integrals, or are we all just sitting there going back to sleep?
Are you talking about the
Oh dear, you're cutting
dx,
out.
dy,
I can't-
dz?
Yes,
I'm sorry, I'm not.
yes, that would be it. D what?
Dx, dy, dz.
Okay, that's an excellent choice. Okay, thank you. Somebody got it. All right, thank you very much for paying attention and being awake. All right, and you guys don't get this, then midterm 3 is not going to be fun. Now, what's another choice? Well, you know, we could say dz, dy, dx, or dy, dx, dz. Any of those 6 choices I've gone over, fine. How about the volume element for cylindrical? We just went over it today. It's r dz, dr, d theta, right?
Right.
Okay, now what about spherical? You're not going to like this. So please know this for the midterm next week. Otherwise, prepare to die. It's rho squared times sine phi times d rho, d phi, d theta. And usually in that order, because we usually don't switch the order on you. So stick to that order. Okay, where'd the rho squared and the sine phi come from? Well, it didn't come out of thin air. It came from the volume of one of these spherical blocks, if you will. I don't want to go through all of that because it would take me some weird time to do it. But basically, if I did the whole partitioning and all this stuff, if you look at a spherical block right there, the volume of that spherical block ends up having that rho squared sine phi in it. Okay, I know, weird. Okay, I'm not going to go over the whole penumbra of a proof for that. Go take a vector calculus class. Let's do something real quick, a quick true false, and then we'll do a quick integral, and then I'll call it. So the triple integral representing the mass of an upper hemisphere centered at the origin with radius square root of 5, where the density function is given by f, which is a function of rho theta and phi, 1 over rho cubed plus 1. So there he is. When you do a mass problem, you always want to put your density function right there in the integrand. That looks beautiful. Is this look like it's going to work? Well, you do have the correct volume element. So this is good. So this is the correct volume element because you've got the rho squared, the sine phi, the d rho, the d phi, the d theta. That looks good. So I claim this is false. Why? Well, theta is going from 0 to 2 pi, which looks okay. Rho is going from 0 to square root of 5, which is good. Rho is never allowed to go negative. But look at what phi is doing. They're basically saying that phi is going between negative pi halves and positive pi halves. And that's wrong-o. Why is that wrong-o?
Because phi is between 0 and pi, I think.
Yeah.
Pi. Yeah.
Yeah. Recall from the whole definition that phi is a very restricted angle. And he's only ever allowed to go between 0 and pi. No other choices. So this is a false, bad triple integral. I don't want to see any of you setting up bad triple integrals because then you'll get in trouble. Okay. So when you're converting a generic triple integral, you know, in rectangular to spherical, the x gets replaced with rho sine phi cos theta, the y gets converted to rho sine phi sine theta, z rho cos phi, and then you're going to have your volume element. So dv is rho squared sine phi d rho d phi d theta, and then you're going to have to put limits on there for whatever. Let's do one problem, and then we'll call it. So here's an integral. It's in rectangular right now. We're going to use spherical coordinates for a reason, because the region Q is the entire sphere given by x squared plus y squared plus z squared equals 25. So it's a sphere centered at the origin of radius 5. So let's do the limits right now. Rho is 0 to 5 because it blossoms out all the way from 0 to 5. If you looked at the trace that this sphere makes in the xy plane as it cuts through the xy plane, that'll help you get your theta. Theta is making a full revolution between 0 and 2 pi. Now here's the hard part. What are the limits for phi? This is kind of weird. Because this sphere is encasing, you know, all the points on the sphere, if you pick any of them, they'll range, you know, when they'll be making the angles, lots of different angles, but they'll start making the angle between the positive z-axis at 0, because some of those points actually live on the positive z-axis, and then all the way down to pi. It'll get the full range of phi. So good news, when we convert to the triple integral, you're going to go rho squared sine phi d rho d phi d theta in that order. So rho will go from 0 to 5. Phi is going from 0 to pi. Theta goes from 0 to 2 pi. And then you convert your integrand to spherical. So that's going to be 1 over rho squared. Now what? Ooh, these rho squareds cancel. Yay! Can you do that? Absolutely. Then you only have sine phi left in your integrand. What's the integral of sine phi with respect to rho? Well, sine phi is constant, so you only have to worry about just the rho going from 0 to 5. But that's just going to be equal to 5. So I'm just going to pull the 5 out in front of the integral. Now I have a double integral. Okay, that's all that's left right now. And we're going to integrate sine phi with respect to phi. Oh, that's pretty easy. It'll be negative cos, and we'll evaluate negative cos between the limits of 0 and pi. Fine. So what's that going to be? Well, what's negative cos pi minus a minus cos 0? What the heck? Negative negative 1 plus 1. Well, that's 1 plus 1, which is 2. So I'm going to pull a 2 out in front of the last integral, and now you're just going to integrate basically 1 with respect to theta, but that's just going to be theta, and theta is going from 0 to 2 pi. So you're like, oh, well, this is just going to be 10 times 2 pi. Final answer, 20 pi. And we're done. There's your first spherical coordinates triple integral. Congratulations. Wasn't too hard, nothing major weird there. We'll do more next time, and then we'll wrap up spherical coordinates completely next time. And then we're going to start chapter 17 on vector calculus.